Oh,
But
there was a different one too.
that's right. Well,
Oh,
hi
I missed
everyone.
that.
Yeah, we're just talking about 3D Experience Live merch or 3D Experience World merch. You'll get to see Shreyas' cool merch from last year in a minute. But hi everyone, welcome back to another episode of SOLIDWORKS Live Design. My name's Noah. I'm a process consultant here at Dassault, working primarily on our X apps. And I'm joined here with my friend and colleague, Shreyas. Shreyas, can you introduce yourself?
Hey everyone, this is Shreyas Vaidya. I am an industry process consultant here at Dassault Systems. I work on our worldwide simulation team.
Awesome. And we're here to bring you the next installment of our Airless Sports Ball series. We have a bunch of exciting things to show you today, everything from design to simulation to manufacturing. So there's no time to waste. What do you say? Let's jump right into it.
Let's do it.
All right. So here. So how did this project even start? Well, a little while back, we did a project on an airless basketball. Wilson introduced this product last year, actually during the NBA dunk contest, and it just went completely viral. There was everyone all over the interwebs designing their own, 3D printing their own, and Wilson decided to actually sell these for a small price tag of $2,500. So, like many people out there, I was like, I think this is so cool, but I'm not about to spend thousands of dollars on a basketball. So I thought, I have a 3D printer, I have the design tools, maybe I could just make one myself. So that's exactly what we did on our last episode. We designed it using SolidWorks, using CATIA, and we 3D printed it, and we had a whole lot of fun. Highly recommend you check out that episode. But then we asked you, the audience, how can we build on that? And so the people spoke, you voted, and a football won out. So these are the results of that poll. And then Shreyas and I got to work. We started working on the football, and this was kind of how that process began. We added a pattern, printed it up, and you might be thinking, well, this is a whole lot similar to the basketball, right? And it is in some ways. Step 2 and step 4 are similar in that CATIA pattern and that 3D print, but step 1 and 3 were very different. First off, with step 3, we have Shreyas here. He ran a bunch of in-depth, complicated simulations, which he's going to share with us, which are really just mind-blowing. They're like eye candy to look at. And the other thing we did differently this time from a design perspective was we used a very different technology to design this football. The original basketball was designed with parametric xDesign, which is similar to desktop SolidWorks, and the football was primarily designed using xShape, which is a subdivision modeler from our friends at CATIA. So this football is a relatively simple design, so it might not look so obvious at first, but the distinction in these two design technologies is really important. We know sub-D sculpting is a completely different CAD animal with its unique strengths. It's freeform. It's this organic way of modeling by pushing and pulling faces. And it's very different from traditional SolidWorks and xDesign workflows. But that doesn't mean you shouldn't be able to leverage all the power that the 3D Experience platform has to offer with roles like 3D Pattern Shape Creator. In fact, this is a perfect opportunity to leverage that type of technology because it's really useful for these kind of hand grips. And the ideal hand grips are organic in shape, right? They kind of form to the contours of your hand. They're not usually so easy to design in parametric workflows. And a perfect example of that is with the rubber grips on this jigsaw with the front, the handle, and the battery. Another great example of this was last year's What's New. We made these handles for a custom bike with xShape to fit to the rider's hands. And then we added different patterns to increase grip strength using xGenerative design as part of the 3D Pattern Shape Creator role. So again, we'll make a simple model today, but the important takeaway is the technology we're going to use is very different from the basketball, and it just adds another layer that you can add to your parametric and pattern workflows. And it's just another tool that you can add to your digital toolbox. So let's jump in and see how we can use it. Something I didn't mention beforehand, we're actually going to set a world record today, and we are going to design the world's fastest football. And I should actually make the distinction, Shreyas, this is an American football, not the traditional one, to be fair to our global audience. So I'm going to start by bringing in a sub D quad ball. Again, this is just an organic environment where you can push and pull faces. I'm going to increase the number of loops so we have more faces to play with. I'll scale it up to 110 millimeters. And here we go. We're in our sub D space where pushing and pulling is the way to get the shape we want. We know football has symmetry to it, so I'm going to go ahead and apply symmetry about the ZX plane. And now you could see whenever I do something to one side, it happens to the other. And so to make my football shape, I want to start out dragging this direction, but obviously I'm not getting the full movement I want. So I could just kind of box select more vertices and drag out that direction, but still it's not giving me the shape I want. Ideally, I want this vertex to be out further than this one, to be out further than this one, and it's going to give me this nice oval shape. And a quick way I can do that is with a command called soft selection. This is going to help us catch the world record here, because I'm going to be able to do this in just one go. And you can see when I pull in one direction, it's expanding the influence of this thing here we call the robot. This allows us to transform, scale, or rotate any entity. And because of this feature in soft selection, I can change how far the radius is to include any adjacent entities that we could then sculpt. So anything that's in blue is not being affected very much. Anything that's in pink is very much being affected by whatever we do with this robot. So I'm going to go ahead and set it to 65 and drag, let's say, yeah, it's called about 60. And there we go, our football shape. Very simple, but you could see how the underlying technology is very different from typical parametric workflows. That doesn't mean that we still can't leverage that parametric technology, because xShape and xDesign, they coexist in this same environment. So let me actually show you here. I created the laces beforehand. Oops, there we go. I created the laces beforehand, and if we take a look at these laces, we can see this is just a standard parametric sketch. This is just like SolidWorks. You know, making those parameters, defining lengths and widths, and extruding it. I extruded it up to the football, and then did a combine tool to get the thickness I wanted. So even though I'm using subdivision technology for the football, I'm still referencing it with parametric technology for the laces. And from there, we're ready to go into our third technology, which is algorithmic technology, where we add this crazy pattern to it. But before we do that, we need to give it a pattern. Or, I'm sorry, we need to give it a surface. And the surface we want to give, of course, is the surface of this football. So I'm going to activate this new OGS, which is just going to act as our folder for when we create this surface. And under our surface tools, I'm going to make an offset. So I'll select one of these, and using tangent propagation, it's going to select all the faces tangent to the one we selected. The distance is going to be 0 because we just want the surface how it is. And from there, we are ready to switch to xGenerative design and create our crazy pattern. All right, now we can see here how different this design environment is. We have all these boxes. These are called operator nodes. And this is a very similar pattern that we did with the basketball. So I'm not going to dive into every single one of these operators, but I am going to show you how this first operator, this input, this is the key. This is what's going to be plugged in and operated on by all of these different operations. So no input selected, we're going to change that by selecting our input surface. And then we can see, or we should see, how we can go down the line and start to activate all of these operators. And each one is going to have a different effect on our input surface. So let's see here. Okay, so we have our Voronoi node operating. Let me hide our original surface. And while this is loading, a good thing to note with xGenerative design is, again, even though it's using a totally different type of modeling, it's algorithmic, we're plugging in sub-D and parametric geometry. So even though it's a different app entirely, it's integrated with the other X apps on the platform and is fully cloud-based. So this is taking a little minute to load. Let me see if I could switch to, okay, so here's another football we had made previously. And in our design sequence, you should be able to see, okay, so here are all of our operator boxes with our triangulate, our Voronoi pattern. We added an offset curve to give each one of these Voronois a little bit of thickness. And then we thicken the pattern inward to go from 2D to 3D and give this geometry some thickness. So that's how we made that original pattern. Let's see if this is still loading. Looks like we lost connection, but I still have this back up here. And so the key is when we then bring this back into xShape, we're going to be able to combine all of that geometry using a standard combine tool. So you could see here, we took our xgen body that we made with 3D pattern shape creator. We took the laces that we made in xDesign, and we took all the references that we made from xShape and combined them into one shape. And that's how we got to this kind of final football model, combining 3 different technologies all on the cloud. And then we got to a point where we were finally ready to run some crazy, wild simulations on it. So that's where I'm going to pass it off to you, Shreyas, to kind of see all the eye candy that went into simulating this model.
All right, awesome, Noah. That was that was great. Every time I see the X apps in action, I am amazed, especially the ones that let you create patterns, these crazy patterns. I am amazed. I'm mind blown. One thing I can tell you for sure, Noah, is, and again, I'm not a big CAD person, but if I were to design something like this in SolidWorks, first, I don't know how to do it. Second, I'm pretty sure I'll be spending a day or at least a couple of days, coming up with what you just did in like 10 minutes.
Well, I'm glad you like it, man. But I really want to see kind of these crazy simulations you made. I could look at those all day because those were just
all right. Let's jump right into it then. So, all right. So now that we have our design in our browser-based CAD tool, what I'm going to do is start from my browser itself, right? So we're sharing a same collaborative space. Both me and Noah, we're working in the same collab space. So whatever he works on, I have access to the same collaborative space as well, which kind of helps me, in getting access to the geometry as soon as Noah has finished working on it, right? But one thing I want to make sure is, and again, I'm in my web browser right now. One thing I'm going to make sure is I'm going to branch out this design. So basically make a copy of it so that when I'm working on my simulations, accidentally, I don't want to mess anything in Noah's original design. So that's basically what I did, all using my browser. Even the simulation apps can be launched using the browser as well, as you can see here. Just to quickly verify, the design is more or less similar or the exact same design that Noah has shared with me. So what I've went ahead and done is I've actually set up a flow analysis case, and just to give you a background why we want to do this, right? So uh, this is a football or an American football, right? Just to make it clear. So one of the important plays in a football game is basically the long passes that you can make. Right now, again, quick disclaimer: I'm not a football nerd. I don't follow a lot of football, but one thing I know for sure is the longer you throw, the higher your chances are to score in points, right? And that's basically what we are trying to address here. Is this concept design that we have came up with, is it easier to throw, or is it easier to make those long passes? How easy it is to spin this ball, give it a certain spin rate, give it a whip, throw it in a similar manner the conventional football will travel. And that's what we are finding out. So what I'm going to do is I'm going to use the computational fluid dynamics solution we have on the 3D Experience platform, and set up a flow analysis case and try and understand what are some of the drag forces because of these patterns, because of this change in design. What is the force it takes to actually give the ball a certain spin rate? That's exactly what we're going to find out. So the setup I have here is something I'm going to walk you through real quick. So as soon as I have this design from Noah, what I went ahead and did is I actually created a rotating region around the ball. Now, remember, there's two different things. I'm throwing the ball at a certain angle, at a certain in a certain direction, but I'm also giving it a certain spin rate. I'm pretty sure those of who you follow football know how important that spin rate is. Some of the fastest throws recorded are around 60, 70 miles per hour, and also have a spin rate of around 600 turns per minute. It can go as high as 650, 700 in some cases. So that's the rotating region. It's basically a geometry I've modeled around it. So the spin rate, or basically what we are going to do with this rotating region is we are going to simulate the fluid being rotated as the ball spins. And in addition to this, now the air around the ball can be infinite, but we practically cannot model it in a simulation. So what I've went ahead and done is I've created a bounding box. It's basically my enclosure within which all the fluid action is going to happen. And I'm kind of breaking down that infinite volume into a finite volume. Talking about which, I have also went ahead and discretized this, still a fairly big volume. So I'm going to quickly show you how the mesh on it looks like. Let's do a quick cross section. So you'll get a quick idea about how we are discretizing this, finite volume we have created. I'm going to put this in side mode, maybe zoom in on the ball, and you can see how well the meshing technique in these, simulation apps for CFD simulation helps you capture some intricate geometric details. So we use a meshing technique called body fitted meshing, which helps you to capture those patterns, in this case, with much more accuracy. All right, so that's more or less our simulation setup, or model setup. In terms of our analysis case, though, what I have is, I'm going to quickly walk you through that too. It's pretty easy. So I have a certain inlet velocity applied on one face of the bounding box. So we are throwing the ball at around about 60 miles per hour. As I said, that's more or less how the velocity at which these balls can be thrown. These are the higher ranges. So 60 miles per hour, 27 meters per second. And then I have some outlet pressure applied here. The important thing to note here is we're giving a certain spin rate to the ball, right, or to the rotating region. So that's around 600 turns per minute. That's pretty good if you if you follow football and know some of the higher spin rates that these balls can carry at any given time in these long passes. All right, so that's my setup. Now, one thing I quickly want to also mention is, for the sake of this demonstration, I've actually already ran this simulation. And I want to quickly highlight what the way I've done this. So with the 3D Experience platform and the simulation roles, I can actually go up to 144 cores. Now, for a problem like this, 144 cores or zero 0.5 terabytes of RAM is probably not required, but the option is there. For example, this model that I ran has around about 1.5 million elements. That's still a big size model. But yeah, I ran it using 36 cores, and it took around 5 minutes to go from start to finish and give me a converged solution. And you can run these analyses, multiple analyses cases parallelly as well. So the horsepower is there for you to leverage on if needed. And the good part about this, probably one of the most important thing to note as well, would be the flow solution that I'm highlighting right now. It actually comes with 16 cores embedded. So with your license, you get 16 cores out of the box locally as well as on the cloud. All right, let's take a look at some results. I know this is what everyone is looking forward to. So what you're looking is a 2D plane, 2D cross-section of that fluid domain we have modeled, right? And what you see here on the screen, the plot you see here on the screen is the velocity plot. So you see how the velocity, changes throughout the fluid domain as the ball moves from right to left with a 60 miles per hour velocity and an angular rate of 600 turns per minute. Now, the thing that caught my eye the very first time I simulated this was basically the patterns on it, which also means that it has a lot of holes into it. So it's not like your conventional ball where everything is enclosed, the surfaces are enclosed. With the patterns, air has the opportunity to kind of flow through the ball, which is, I know, unheard of, but just this concept that we're working on, the airless concept, kind of makes it easier for the air to move through the ball as the ball spins, rotates, and cuts through the air. So that can cause some issues, right? Again, what we're trying to do is trying to virtually simulate the performance of this ball in real world. Try and understand the concept design. Is it close? How close it is to a conventional football? So right off the bat, you can notice by plotting these streamlines, there are some streamlines, especially when near to the ball, that actually go through the ball because of these holes, because of these patterns, right? And also remember, the ball's rotating anti-clockwise or clockwise in this case, which means as the air comes near the ball and passes through the ball, it's going to try to rotate along with the ball too. So there's certainly some disturbance, some air disturbance in and around the ball, which is probably not the most ideal thing. And you'll know why, because we'll quickly also check how the conventional ball behaves. But in order to find out what's actually going inside the ball or within the ball, again, this is not an air-filled ball. This is an airless ball. So what I'm doing is a quick cross-section about the XZ axis this time around. And you can see some action that's going on within the ball, right? So you have, this is the velocity plot we're looking at right now. And if you notice carefully the velocity, and I'm probably turn on the original geometry as well so that you know what I'm talking about, especially the 2D cross-section of the ball. So you'll notice that the velocity is drastically changing from the center of the ball and as we move away from the ball. So there's about 15, 16, up to 18 meter per second velocity at the center. And then as you move away, it tends to die down, which means things are looking fairly turbulent within the ball, right? Within the enclosure of this airless ball. And that is something we can also quickly verify with the pressure plot too, right? For example, there are some regions within this ball which has, looks like it's negative pressure. So the air's going to try and suck into the ball. Again, remember the speed of this ball is really fast, right? It's 60 miles per hour. not just in the direction it's traveling, but also it's rotating at a pretty high velocity, spinning at a pretty high velocity. And this is confirmed using these velocity vectors. You see the direction of the air immediately close to the surface of the outer surfaces of this ball, or these patterns. Okay, and again, just to show you, what I'm talking about, the original geometry, and what the plane in the reference that we are looking at. All right. So now that we know there's a lot of turbulence going on, especially with the design, the conceptual design we have. What I'm going to try and do is compare it with a conventional football. So a conventional football, which basically is enclosed, right? So you don't have any holes in it. You don't have any patterns on it. The air's not going to go through it. All it's going to do is try to move around it, and just the shape of it, which is very aerodynamic, makes it easier to travel longer distances. And that's what we are trying to see here, how the conventional ball really behaves. Now, plotting some streamlines real quick, give you an insight into how smooth these streamlines are. There are a couple of lines, right next to the ball, which tend to deviate as it flows through the air. But again, remember, the ball has a angular velocity of 600 turns per minute, which is pretty high too, and that kind of makes those streamline near to it flow or deviate a bit away. But now, looking at the drag forces, and we're going to do some comparison, right? So right now, what you see here is for a conventional ball, you have a drag force of about, and if I'm going to go to my laser pointer here and try and see if I can highlight that to you. It's about 0.73 newtons. So not too high, but that's the number we are targeting, right, for the drag force and our airless concept. And let's take a look at our airless concept and the results from the airless concept in terms of the drag force. So I'm going to highlight, use my laser pointer again. So you have obviously 0.73 for your conventional ball, but then you have about 3.1 Newton for your airless design. So that's significantly higher. If I did that math correctly, it's around about 4 times higher, and we'll see that comparison in just a bit here. But yeah, so definitely the drag forces are a bit higher on our concept design. Okay, so what if let's do a what if scenario. Okay, what if based on the simulation results I'm looking at, I want to go ahead and make a change, right? Because our designs are always iterative. The goal of working on these concepts is to always improve them in terms of performance, right? So that's basically what we went ahead and did. So I communicated this with Noah, and then Noah was, again, as he was fast, you saw, right, how fast he was. He basically went back to these browser based application. He changed our pattern size from 10 millimeters to 20 millimeters. So now you have bigger patterns, as you see here. This is the red one is our old one, old concept one, and the one that you see here on the screen is our second design concept. So we have bigger patterns. What we are hoping here is the drag might reduce. The air has more room to diffuse out of, or get into and diffuse out of the ball. So we are hoping, we don't know yet, we are hoping that this might just do the trick for us. I went there too fast. Let me go back here. So
just a question for you, Shreyas.
Yeah, sure.
You're showing all these just mind-blowing simulations. Are these all a part of the same app and the same role, or are you going in between different?
That's a great question, Noah. So you probably didn't even notice. So I'm actually going between apps, right? But it's all the same user interface. These are on my local machine, but some of the apps you use for design, they are on a web-based, those are web-based apps. So they're on a browser, but they talk to each other, right? So they have they can communicate with each other. So and that's basically what I wanted to highlight here real quick, that hey, look, even though we have a design change, all you have to do is either relaunch the model or just do a quick update so that your designs, or your simulation models are up to date with your CAD models, right? But I know what some of you are wondering. What happens when my CAD model changes, right? What happens when the geometry changes? Does it affect my simulation? Yes, it definitely does affect your simulation results, but it does not affect your simulation setup. So as long as you're not changing your geometry drastically, in this case, we still went from a 10 millimeter to a 20 millimeter change. It did not affect our simulation setup. All I had to do was update my simulation and rerun the model, and that's it. So let's take a look at some results real quick. This is a side-by-side comparison of how a conventional ball performs versus how our concept one performed, and then how a design change, which was our concept two, performed. So I'm going to quickly highlight the drag force, which was one of the key metrics we were after. So the drag force on the conventional ball, or rather on our first concept, was about 4.2 times higher than the drag force on the conventional ball. So that's significantly higher. And also with our design change, things actually got worse, as you can see. See, I told you we don't know it for sure, and that's basically the beauty of simulation, and helps you get those key insights that you would not be able to guess. So simulation gives, basically can help you understand how your products really perform in real world scenarios. So that's pretty much it in terms of simulation. That was a quick run through of what I was able to do with these two concepts. I'm going to hand it back to Noah. I know he did go ahead and print the concept one for us. So we'll hand it back to you, Noah, to give us a quick run through of how you print it and how does it perform when you're able to do some throwing with this ball.
Awesome. Let's do it. Thanks so much, Shreyas. And again, to your point on going updating all your simulations when we made that design change, I remember going through it with you, and we were kind of shocked how you didn't even have to close and reopen the file. We just clicked refresh from your side, and all of my changes immediately propagated. You had a new football, a new design right there.
That is exactly right. Yep.
So that was really cool, and just made our jobs a little bit easier. And you're 100% right. We went ahead and printed that first iteration. Again, we use standard FDM technology. So this is just a desktop 3D printer. And I still think it's pretty mind-blowing, the level of detail and the quality you can get from these desktop machines, even like $300-400. We were able to print this football and capture all of the complicated detail that came along with this crazy Voronoi pattern. So we did that, and the material as well, very affordable. I printed it on my Prusa Mach 3. I used a Sane Smart TPU material. I got it off Amazon for around $20-30. And I can't say enough good things about it. The football was super durable. It printed very well. One setting I did have to change, if you decide to print this yourself or print with any TPU material, is avoid crossing perimeters. So TPU can get a bit stringy. After your parts are finished, it can kind of have like these little hairs on them that you could kind of burn off with a lighter. But if you avoid crossing perimeters, it actually reduces the amount of stringing you get on that print. So we had a question in the chat. I have it right here. 20 hours to print was the final time for this football. In comparison, the basketball took around like 45 hours, so a little bit more than double. And the only other slicing setting I changed was to add support. I added this organic support on the bottom so I could make sure all those steep overhangs printed. I could have cut this football into pieces and avoid support altogether, but we remember how that went with the basketball. Shreyas's simulations actually confirmed that when we dropped the basketball, it broke into a million pieces. So we were not going to go that route this time. We were going to print it in one part, one go. And then we just started testing it out. It was super fun to play with. This is me and a buddy of mine testing it out on a field by me. And it was a lot lighter than a traditional football. So it felt like you could throw it a lot further. But one of the things that Shreyas' simulations confirmed was because there's all this air coming inside of the football, coming through the inside of the football, it creates all this turbulence, and it kind of makes the footballs die down when it's at its height as you're throwing it. So if you try to launch this thing as far as you can, when it's at its peak, instead of continually traveling like a standard football, it kind of just kind of gives up in the middle of the air. So that was definitely confirmed by Shreyas' simulations. But it was really fun to play with, really fun to throw. And then we just got thinking, it feels durable, this TPU plastic. Can we even like break this thing? So we just started throwing
Noah,
it.
can I ask a quick question though on that previous video, which I thought was really interesting insight from you. Is it any better to give it a whip? Is it any better to give it a certain spin rate or a higher spin rate than a conventional football?
Great question. So we tried giving it a spin, throwing it like a regular spiral, as you would with a regular American football. But because of all the air that's creating all that turbulence, it's a lot harder to get that spiral. So it kind of wants to do this wonky movement. So that also could have contributed to not being able to throw it as far, even though it was much lighter.
Interesting.
But great question. But like I was saying, then we just started testing the durability. We started just throwing this thing as hard as we could at a concrete wall to see if it broke. And not only did it not break, but I have the original one here. This thing doesn't even have a scratch on it. It's just as sturdy as it was when it came off the build plate. And we were throwing this thing really hard at the concrete, just kind of spiking it as if we had just scored a touchdown. And it really doesn't even have a scratch. So it's crazy to think not only how durable this TPU material is, but how strong the layers are that are bonded together as they're printing. And it also, I think, speaks a lot about this Voronoi pattern. We chose this pattern with the basketball and the football for a reason. It's known as a very strong pattern that maximizes strength while also taking away weight. So those were our findings with the manufactured ball. It looks like we have a couple questions in the chat. What do we have here? We were able to achieve the tight spiral. Did it deform a lot when catching? Good question from Gian. Did it deform a lot when catching? So as you can see, you can deform it pretty easily. Maybe for a next version, we can make the inside a little bit thicker so it doesn't deform as much. When you catch it, not really. It's pretty solid when you initially catch it. You can only really deform it if you really try to. So I think it had just enough stability where catching it didn't deform it. But I definitely would want to go a little bit thicker and make it easier to kind of catch, give it more weight to throw as well. But I think that's it from the manufacturing portion, Shreyas. I know
Awesome.
You had a couple more things to plug on the simulation side, right?
Yeah, I just want to show a quick call to action, or I have a quick call to action for our audience. So if you like what you saw with simulation, we do have this webinar series we run on a monthly basis, which is called the 3D Experience Works Simulation Webinar Series. So what we do is we invite our existing customers to talk about their journey, their products, their workflows, and how they're using simulation tools offered by Dassault Systems in their day-to-day activities and solving really challenging problems. So if you're interested, we have these webinars every month. The links to these webinars are on the website, on SolidWorks' website, or what you can also do is scan this QR code, and it should take you directly to our SolidWorks website and the landing page for these webinar series. But yeah, that's pretty much it from my side.
Awesome. And I see Juan's comment in the chat. I can confirm now we will be bringing either the full size one, maybe the small one as well, to 3D Experience World. Then we see everyone. So you could get to play with it, Juan, and anyone else. If you're able to join us in Dallas, we'll have these as well to maybe throw around the showroom.
Yeah, let's print a few more, and we can basically put it on display at World. Yeah, that's a good idea.
Definitely.
All right, awesome. So yeah, that's pretty much it from our end. Thank you very much for joining us. We appreciate your time today.
And I think we do have a next episode to plug as well.
That's right.
SOLIDWORKS Live will be back. Is it the 26th?
That's the 26th. So what's new 2025, September 26th, 11 a.m. Eastern. So don't forget to join us then.
Awesome. Thanks so much, everyone.